You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts, as well as our very own Worth Electronic technical specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. During the design phase, time is money. And if you're in a time crunch, you might not be able to hammer out an inductor design and may rely heavily on design software from the manufacturer or an off-the-shelf solution. Now, the relevant design software from semiconductor manufacturers serve to reduce development times. And with software like Red Expert, you get a tool that identifies the right inductance for a buck or boost converter very quickly. But what if you can't find that off-the-shelf solution? Today, we are going to discuss a few tips and tricks on creating a power inductor and even give a practical guide for the selection of power inductors for DC to DC converters. We'll start by looking at the switching frequency. Now, the switching frequency of typical converter ICs in the market is in the range of between gigahertz. First generation regulators operated in the range 30 kilohertz to 55 kilohertz. This leads to our first design tip: find suitable core materials. For switching frequencies under 100 kilohertz, you should use iron powder, ferrite, superflux. And from Worth Electronic, the PERM series is suitable. For a switching frequency between 100 and 1000 kilohertz, you could use ferrite, superflux, and again, the PERM series. And finally, for a switching frequency of greater than 1000 kilohertz, it's best to use ferrite. The PERM is suitable for all three types of switching frequencies. Next, we need to look at the inductance value. Now, if there's no application note or software available, inductance can be calculated using the following rule of thumb formula. For a step-down regulator, the inductance equals the maximum input voltage minus the output voltage times the output voltage plus the duty cycle voltage all over the maximum input voltage plus the duty cycle voltage times 0.3 times the output current times the switching frequency. For the step-up regulator, the inductance equals the output voltage plus the duty cycle voltage minus the minimum input voltage times the input voltage squared all over 2 times 0.2 times the output inductance multiplied by output voltage plus duty cycle voltage squared times the switching frequency. Now, if you weren't able to follow all of that, have no fear. This formula is shown as figure 1 attached in this podcast. With the ripple current factors 0.2 to 0.4 selected as 0.2 and 0.3 in this example, the output inductance is the operating current of the circuit to be supplied. Standard values for the inductance can be selected on the basis of the calculated value. Now, if you get the value of 37.36 microhenry as the result, you would typically select the standard values 33 microhenry, 39 microhenry, and possibly even 47 microhenry just for testing. Our second design tip is about the inductance value. The higher inductance, the smaller the ripple current. The lower inductance, the higher the ripple current. The ripple current is essential in determining the core losses. Besides the switching frequency, it plays an important parameter for minimizing the power loss of the power inductor. Next, we look at the inductor current ratings. The current load for power inductors can be calculated very accurately in terms of DC current load and ripple current load or core losses using our simulation software. For a rougher calculation, however, for a step-down regulator, the nominal current of the inductor equals the output inductance, and the maximum coil current equals 5 times the nominal current of the inductor. For a step-up regulator, The nominal current of the inductor is equal to that of the output voltage divided by the input voltage and then multiplied by the output current. The maximum coil current equals 2 times that nominal current of the inductor. Our third design tip here is to look closely at the definition for the datasheet specifications because manufacturers can vary greatly on this. The nominal current for power inductors is usually linked to the specified self-heating with DC current. Here, the self-heating of plus 40 degrees Celsius is common at the nominal current. According to the semiconductor manufacturer's recommendations, the saturation current is the point at which the inductance value has fallen by 10%. Now, unfortunately, this is not a standard value for power inductor datasheet specifications, and this often leads to misinterpretation among the users. Then we take a look at DC resistance. Once the required values for inductance and inductor currents are calculated, you select a power inductor with the minimum possible DC resistance. Here, the demands are often counteractive: small size, high energy storage density, and low DC resistance. Using suitable winding methods and the new series, such as Worth Electronics WE-HCI and the WE-PDF flat wire inductors, this ideal case is very close to what we hope to achieve. The datasheet definition must also be looked at here. We need to ask ourselves, is the DC resistance specified as a typical value or as the maximum value required for calculating the circuit under worst case conditions? And this brings us to our fourth design tip: DC resistance with the same size. For higher inductance, get higher DC resistance. Lower inductance gets lower DC resistance. And the same inductances for a shielded inductor get lower DC resistance. The DC resistance is essential in determining the wire heating losses, and this is another important parameter for minimizing the power loss of the power inductor. Next, we're going to take a look at the type and the EMC. Magnetically shielded power inductors, such as the WE-PD or the WE-HCI, are recommended for EMC critical applications. The shielding prevents uncontrolled magnetic coupling of the windings with neighboring conductor tracks or components. Now, this gets us to our fifth design tip, which is use a magnetically shielded power inductor if at all possible. Do not route any conductor tracks under the component and do not place any circuit boards directly above the component, as this could give rise to coupling via the air gap remaining. Unshielded power inductors, such as the WE-PD2, can be used for uncritical applications or for low power circuits. Many packaging series can even be changed from shielded to unshielded versions while maintaining solder pad compatibility. Our sixth tip is about the advantages and the disadvantages of magnetically shielded inductors. Now, one of the advantages of magnetically shielding the inductor of the same type is that the higher inductance value means lower DC resistances for the same inductance, which equals lower wire losses. The disadvantage of magnetically shielded inductors of the same type are that we only get slightly increased core losses due to a larger core volume. Given correct dimensioning, the core losses remained lower. Next, we'll discuss the LC filter. Now, an LC filter at the DC converter output is recommended if a low noise output voltage is required. For our seventh design tip, we recommend selecting a cutoff frequency at 1/10 of the switching regulator frequency, and then selecting the output capacitor, for example, 22 microfarad, and finally calculating the inductance. Our equation turns out to be the inductance equals 1 divided by 2 times pi times the switching frequency, all squared, times the capacitance. And our eighth and final design tip is about the ripple measurements. To properly measure ripple on either input or output of a switching regulator, a proper ring in tip measurement is required. Standard oscilloscope probes come with a grounding clip or a long wire with an alligator clip. Now, unfortunately, for high frequency measurements, This ground clip can pick up high-frequency noise and erroneously inject it into the measured output ripple. The standard evaluation board accommodates a homemade version by providing probe points for both the input and the output supplies and the respective grounds. This requires the moving of the oscilloscope probe sheath and the ground clip from a standard oscilloscope probe and then wrapping a non-shielded bus wire around the oscilloscope probe. If there does not happen to be any non-shielded bus wire immediately available, the leads from axle resistors will work. By maintaining the shortest possible ground lengths on the oscilloscope probe, true ripple measurements can be obtained. The power inductor selection tips described here are based on data sheet specifications. Worth Electronic components are listed in most leading semiconductor manufacturer software solutions and are immediately available for simulations. Corresponding assembled design kits can help optimize prototypes and speed up the design process. Find all design kits available at Worth Electronic online. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on our topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.